In the architecture of the cosmos, we are conditioned to look for the light. We construct our models of the universe by mapping its luminous matter, tracking the galaxies, quasars, and brilliant stellar nurseries that punctuate the dark. But, in the autumn of 1981, an astronomer named Robert Kirshner at the University of Michigan reviewed data from a recent redshift survey and discovered a mathematical impossibility. He found a region of the sky, spanning several degrees, that defied every existing model of cosmic topology. It was not a cluster of unusual galaxies, nor was it a region of sparse stellar distribution. It was a staggering, inexplicable absence, where the data should have indicated the slow, steady scatter of galactic light stretching across the cosmos. The charts simply stopped. Kirshner had located a stretch of empty sky in 3 separate directional vectors, all aligning at the identical distance, all refusing to contain the matter dictated by the laws of physics. This was not a calibration error. It was not an artifact of the survey parameters. It was the preliminary detection of what is now recognized as one of the largest macroscopic structures in the observable universe. And it is a structure constructed entirely out of nothing. To comprehend the magnitude of this anomaly, we must first examine the methodology of cosmic cartography. As a species bound to a single solar system, we cannot launch probes to neighboring galaxies, nor can we physically traverse the interstellar medium to verify our models. Every data point we possess regarding the large-scale structure of the cosmos is derived from the behavior of electromagnetic radiation. Specifically, we rely on a single, critical property of light known as redshift. As the universe undergoes metric expansion, the very fabric of space between galaxies stretches. Light traversing this expanding space is stretched along with it. A photon emitted with the high frequency of blue light will, after traveling for hundreds of millions of years, have its wavelength elongated into the red spectrum by the time it strikes our orbital telescope mirrors. The further an object lies from our observation point, the more severely its light is stretched. By quantifying the redshift of a distant galaxy, astrophysicists can calculate its precise distance and recessional velocity. This technique, known as a redshift survey, is the empirical foundation of our three-dimensional map of the universe. In 1981, Kirshner, alongside his colleagues at Yale and the Mount Wilson Observatory, deployed a highly specific observational methodology known as a pencil beam survey. They selected 3-minute regions of the sky, separated by angular distances of approximately 35 degrees. Within these narrow visual corridors, they measured the redshift of every galaxy luminous enough to trigger their sensors. Each observational field covered less than 1 square degree of the sky, yet the redshift data was designed to yield a continuous, chronological column of galactic distribution extending outward from Earth. According to the standard cosmological model of the era, these 3 pencil beams should have returned a smooth, predictable distribution of galaxies at every redshift interval. The galactic density should have gradually thinned at extreme distances, purely as a function of observational limits. But there should have been no abrupt terminations. Instead, the data presented a catastrophic drop-off in each of the 3 fields, at a redshift correlating to a recessional velocity of roughly 15,000 km per second. The galaxies simply vanished. The probability of 3 distinct, widely separated observation vectors encountering a random void at the exact same distance was statistically negligible. Kirshner and his co-authors subsequently published a preliminary report proposing the existence of a massive spatial void in the direction of the constellation Boötes. The astronomical community responded with intense skepticism. In the early 1980s, the paradigm of an isotropic, uniformly distributed universe was only just beginning to fracture. While early high-resolution surveys were hinting at a cosmic web of filaments and clusters, no one had theorized a localized vacuum on the scale Kirshner was proposing. The consensus was that his pencil beam surveys were simply too narrow, acting as a thin and unstable foundation for such a monumental claim. Critics argued that the galaxies were likely present but too faint for the era's detection thresholds, or that the beams had merely grazed the edges of a much smaller, unremarkable gap in the cosmic web. The scientific method demanded rigorous verification. For the next 6 years, Kirshner's team painstakingly mapped the intervening space, aiming to determine whether the Boötes Void was a true cosmological feature or a mere artifact of incomplete sampling. In 1987, the Astrophysical Journal published the definitive follow-up data. The methodology had been massively scaled up, expanding from 3 narrow beams to 283 distinct observational fields distributed across the previously unmapped regions. The team measured the precise redshifts of 239 newly identified galaxies. They then applied a simple, devastating statistical test. Within the specific velocity range that the initial survey had flagged as empty, between 12,000 and 19,000 kilometers per second, how many of these new galaxies should be present? A standard, uniform distribution model predicted that approximately 31 galaxies should inhabit this specific volume of space. The survey returned 0. Not 5. Not 1. 0 galaxies were found in the exact spatial coordinates where the void was hypothesized to exist. The statistical anomaly was now an empirical fact. Let us quantify this absence using the precise metrics of modern astrophysics. The Boötes Void is a roughly spherical region of space, centered at a right ascension of 14 hours and 50 minutes, and a declination of positive 46 degrees. It sits at a distance of approximately 700 million light-years from Earth. Its radius spans 62 megaparsecs. In non-standard units, this equates to a diameter of nearly 400 million light-years. It occupies a volume exceeding 1 million cubic megaparsecs, encompassing roughly 2% of the entire observable universe. Under standard cosmological conditions, a spatial sphere of this immense magnitude should contain on the order of 2,000 distinct galaxies. Despite decades of exhaustive, multi-spectrum observation, the Boötes Void has been confirmed to contain approximately 60. To contextualize this extreme underdensity, we can turn to the analytical framework of astronomer Greg Aldering. He noted that if the Milky Way galaxy had been situated at the geometric center of the Boötes Void, the human species would not have realized that other galaxies existed until the advent of deep space telemetry in the 1960s. The historic 1920s discovery by Edwin Hubble that the Andromeda Nebula was actually an entirely separate island universe would have been impossible. Our entire understanding of the cosmos would have been delayed by half a century, trapped within a localized bubble of profound isolation. However, to classify the Boötes Void as a pure absolute vacuum is a fundamental error in astrophysics. The space within the void is not a true null state. It remains permeated by the cosmic microwave background radiation, trace amounts of dark matter, and diffuse hydrogen gas. What defines the void is its extreme thermodynamic and gravitational failure. It contains approximately 1/6 of the average matter density of the universe. The dark matter that should have coalesced to form gravitational wells is either absent or too diffuse to initiate structure formation. The primordial hydrogen gas never achieved the critical density required to trigger stellar ignition. The void represents a region where the universe, for reasons still being fiercely debated in theoretical physics, simply failed to organize itself. This localized failure of cosmic organization forces us to examine the lambda cold dark matter model, the current standard model of cosmology. This framework predicts a universe structured like a vast cosmic web, characterized by dense filaments, massive superclusters, and intervening voids of varying dimensions. In this model, small and medium underdensities are a mathematical inevitability. The universe is expected to resemble a quantum foam, with matter concentrated along the intersecting boundaries of expanding bubbles. The general morphology of the Boötes Void aligns with this theoretical architecture. It is the sheer, unprecedented scale of the structure that strains the limits of our predictive models. A void spanning 400 million light-years sits at the absolute upper boundary of what the lambda cold dark matter model can comfortably accommodate. Structures of this magnitude require highly specific, anomalous initial conditions in the immediate aftermath of the Big Bang. The current consensus, driven by high-resolution N-body simulations, posits that Boötes is a composite structure. The 60 galaxies discovered within its interior are not distributed randomly. They are arranged in a distinct, cylindrical filament bisecting the void. This internal geometry is a critical diagnostic marker. It indicates that the Boötes Void did not originate as a single, massive underdensity. Rather, it is the result of multiple, smaller voids expanding over billions of years, draining their localized matter outward, and eventually merging into a single macroscopic vacuum. The cylindrical filament of galaxies is the fossilized remnant of the boundary walls that once separated these smaller bubbles. Yet while this merger hypothesis explains the mechanics of its formation, it fails to explain the statistical improbability of its location. Our models cannot predict why this specific region of the cosmos was primed to generate a void of such extreme dimensions. This brings us to a critical juncture in theoretical cosmology. the potential violation of the cosmological principle, formulated by Albert Einstein in 1915 to simplify the application of general relativity to the universe at large. This principle assumes that on a macro scale, the universe is both homogeneous and isotropic. It posits that matter is distributed evenly, and that the cosmos should look statistically identical in every direction, regardless of the observer's location. For most of the 20th century, this assumption was the bedrock of astrophysics. But as redshift surveys grew more sophisticated, the bedrock began to crack. In 1986, Valérie de Lapparent, John Hucra, and Margaret Geller published a spatial map that irrevocably altered our understanding of macrostructures. Mapping over 1,000 galaxies, they revealed that the universe was not a uniform distribution of matter, but a complex, foam-like lattice. We must invert our classical perspective. For decades, astrophysics treated galaxies as the primary subjects of the universe, viewing the empty spaces between them as mere background canvas. The discovery of the Boötes Void and the subsequent mapping of the cosmic web demands a complete figure-ground reversal. The bright structures, the galaxies, the quasars, the superclusters, occupy a negligible fraction of the universe's volume. Current spatial analytics indicate that voids account for roughly 80% of the observable cosmos. The galaxies are not the structure of the universe. They are merely the luminous boundary conditions of the voids. The universe is a collection of massive, expanding vacuums, separated by incredibly thin membranes of accumulated matter. These voids are not passive, static, empty spaces. They are highly active kinematic drivers of cosmic evolution. As the universe expands, the negligible matter within a void continues to flow outward, migrating toward the denser gravitational environments of the surrounding walls. Consequently, over cosmic timeframes, the walls grow denser, and the voids grow emptier. The voids effectively act as repulsive gravitational centers, pushing matter outward in a slow, billion-year exhalation. The Boötes Void is currently in the midst of this kinematic expansion. In another billion years, its internal filament will be entirely cannibalized by its edges, rendering it even larger and more profoundly empty. This dynamic expansion introduces a localized variable that may distort our most fundamental cosmic measurements. Consider the KBC void hypothesis, proposed by observational astronomers Keenan, Barger, and Cowie. Their data suggests that the Milky Way itself, along with our entire local group, may be situated near the center of a massive 2 billion light-year underdensity. If this hypothesis holds true, the implications for modern physics are severe. It means our measurements of cosmic expansion are fundamentally biased by our gravitational environment. Matter inside a void is pulled outward by the denser perimeter, creating a localized velocity vector that mimics accelerated expansion. This localized gravitational lensing effect offers a compelling, albeit highly contested, mathematical framework for resolving the Hubble tension. The persistent discrepancy between the expansion rate measured via the cosmic microwave background and the rate measured via local supernovae. Furthermore, the integrated Sachs-Wolf effect suggests that these massive underdensities leave a thermal imprint on the cosmic microwave background itself. As photons traverse a supervoid, the decay of the local gravitational potential causes them to lose energy, registering as anomalous cold spots in our orbital telemetry. The Eridanus supervoid, potentially even larger than Boötes, is currently the leading candidate for explaining the most prominent cold spot in our microwave maps. We are left with a cosmological framework that is highly dependent on the observer's spatial coordinates. If our fundamental metrics of cosmic expansion are being warped by the gravitational deficit of our own localized vacuum, we must ask whether the observable universe we have so meticulously mapped is an objective reality, or merely an optical illusion generated by the geometry of nothingness. This inversion of perspective forces a complete re-evaluation of macrocosmic architecture. For most of the 20th century, when astrophysicists and cosmologists drafted maps of the large-scale universe, their models were fundamentally galaxy-centric. The academic focus was overwhelmingly anchored to luminous matter, the fusion reactors where stars ignite, where planetary systems coalesce, and where gravity compresses baryonic matter into structures easily captured by our optical and radio telescopes. The vast expanses between these galactic clusters were mathematically treated as a passive backdrop, a dark and inert canvas upon which the actual architecture of the cosmos was painted. The voids were acknowledged, certainly, but they were not the subject of inquiry. The subject was always the light, the mass, the localized coordinates, where thermodynamic and gravitational events were actively occurring. However, what the discovery of the Boötes Void initiated and what subsequent decades of high-resolution redshift mapping have quantitatively confirmed, is a subversion of this fundamental premise. The observational data dictates that our historical model had the figure and the ground entirely reversed. This structural paradigm shift was solidified in 1986 when astronomer Valérie de Lapparent, collaborating with John Hutra and Margaret Geller at the Harvard-Smithsonian Center for Astrophysics, published a redshift survey that fundamentally altered the trajectory of modern cosmology. Rather than measuring isolated luminous points across a scattered grid, their methodology involved mapping a precise, continuous, angular slice of the sky containing over 1,000 individual galaxies. The spatial distribution returned by their telemetry was unmistakable, and it definitively shattered the assumption of a uniform, isotropic universe at intermediate scales. The galaxies did not exhibit a smooth, Poisson-like distribution. Instead, they self-organized into highly defined two-dimensional sheets and dense, one-dimensional filaments. Bound between these luminous boundaries were colossal regions of absolute emptiness. The universe, at the scales measurable by their instruments, was not a homogeneous fluid. It was a foam. The Boötes Void, initially detected 5 years prior to the de Lapparent map, but only fully contextualized afterward, served as the ultimate macroscopic evidence for this foam-like geometry. Once this porous topology was established as the empirical reality of the observable cosmos, the academic inquiry evolved. The operative question was no longer whether such voids existed, but rather, what physical mechanisms governed their maximum volume, what forces defined their boundaries, and what structural role they played in cosmic evolution. The preliminary theoretical framework utilized to explain the Boötes Void was heavily grounded in statistical mechanics and quantum field theory. The cosmic web, according to this model, is the macroscopic derivative of microscopic quantum fluctuations that occurred during the inflationary epoch of the early universe. In the first fraction of a second following the Big Bang, quantum mechanics dictated minuscule variations in the energy density of the primordial plasma. Certain spatial coordinates emerged with a matter density marginally higher than the cosmic mean, while adjacent regions were left slightly sparser. As the universe underwent metric expansion over the subsequent 13.8 billion years, gravity acted as an amplifier for these microscopic discrepancies. The overdense regions exerted a stronger gravitational pull, systematically accreting baryonic and dark matter from their surroundings to eventually form the superclusters and galactic walls we observe today. Conversely, the underdense regions, lacking the requisite mass to generate a competitive gravitational well, were systematically evacuated. They fell behind in the cosmic accretion process. Their matter drained outward, transforming them into expanding voids. Under this statistical model, the Boötes Void was interpreted simply as a region that originated with a minor primordial underdensity, a localized deficit that compounded over billions of years until a microscopic quantum fluctuation ballooned into a spherical vacuum spanning hundreds of millions of light-years. Yet observational data once again outpaced theoretical assumptions. The hypothesis that Boötes was a singular, monolithic underdensity was directly contradicted by high-resolution scans of its internal geometry. In 1996, a research team led by Arpad Zomoru at the Kaptein Astronomical Institute in the Netherlands, in collaboration with J. H. van Gorkum at Columbia University and Michael Gregg at the Lawrence Livermore National Laboratory, executed an extensive radio astronomy survey. Utilizing the Very Large Array, VLA, in New Mexico, they targeted the 21-centimeter emission line of neutral hydrogen within the void. This specific radio frequency, generated by the spin-flip transition of the hydrogen electron, allows astronomers to detect cold, non-luminous gas clouds that optical telescopes cannot resolve. Detecting this faint spectral signature at a distance of 700 million light-years required pushing the VLA's signal-to-noise ratio to its absolute operational limits. Their survey mapped approximately 1% of the void's total volume, specifically targeting coordinates where faint optical signals had previously been detected. The telemetry returned an anomaly that defied the standard model of a smooth vacuum. The galaxies residing within the Boötes Void were not scattered randomly, nor were they drifting uniformly through the empty space. They were highly organized into localized groups, binary pairs, and miniature clusters. The interior of the void was not a featureless absence of matter. Instead, the VLA data revealed a distinct cylindrical filament of galaxies running directly through the center of the void, while the remaining volume surrounding the structure was genuinely, profoundly empty. 1 year later, in 1997, astronomer Greg Aldering, whose primary research focused on supernovae and macroscopic voids, directed a follow-up observation campaign that identified an additional 53 galaxies within Boötes. The spatial coordinates of nearly every single newly discovered galaxy aligned perfectly with this central filamentary structure. The total galactic population within the void rose to approximately 60. A statistically insignificant number for a volume of space that, under normal cosmic density parameters, should have contained upwards of 2,000 galaxies. However, it was not the low quantity of galaxies that proved revolutionary, but their specific kinematic arrangement. These 60 galaxies were not positioned where fluid dynamics equations would place them if the void had expanded from a single, isolated primordial underdensity. Instead, their spatial coordinates perfectly matched the mathematical predictions for a merger event. The cylindrical filament was not an anomaly. It was a boundary layer. This realization gave rise to the current prevailing cosmological explanation, the merger model. In this modern framework, the Boötes void is not a singular empty region that expanded uniformly. It is the composite result of multiple, smaller, distinct voids that expanded simultaneously over cosmic time. As these adjacent voids grew, they systematically evacuated their internal matter outward into the walls between them, eventually colliding and coalescing into a single supervoid. The cylindrical filament of galaxies bisecting Boötes is the physical relic of that massive merger, a structural fossil marking the exact boundary where several smaller voids join together. The fluid kinematics of this process are mathematically analogous to the coalescence of soap bubbles, where the surface tension at the point of intersection temporarily forms a visible membrane before being entirely absorbed into the larger geometric structure. Under the parameters of the merger model, the Boötes void is not a violation of physical laws, nor does it require modifications to the lambda cold dark matter, lambda CDM, standard model. It is a highly standard product of cosmic evolution, merely representing the extreme upper limit of the statistical distribution of void sizes. High-resolution supercomputer simulations of cosmic web evolution, seeded with initial density conditions derived directly from the cosmic microwave background, successfully reproduce voids of comparable scale and internal filamentary structure. However, while the physical mechanism of its formation is understood, its existence mandates a radical redefinition of what constitutes structure in the universe. The luminous formations we observe, the superclusters, the galactic walls, the intricate web of baryonic matter, occupy an almost negligible fraction of the universe's total volume. Quantitative spatial analysis indicates that voids account for approximately 80% of the observable cosmos. The precise size distribution of these voids serves as a critical cosmological probe. By measuring the geometry and expansion rates of voids across different redshifts, astrophysicists can extract independent constraints on the equation of state of dark energy, as voids are the regions where dark energy's repulsive force is least contested by local gravity. The galaxies are not the structural foundation of the universe. The galaxies are merely the boundary conditions. They represent the extremely thin, high-density membranes and curving threads where matter has been compressed against the surfaces of expanding vacuums. The cosmos, at the maximum scales we are currently capable of measuring, is not a collection of massive luminous objects separated by empty space. It is a vast collection of expanding empty spaces, separated by microscopic, two-dimensional surfaces where matter happens to have settled. This is not a philosophical metaphor. It is a mathematically rigorous, quantitative description of the cosmic web. Consider the Hercules Corona Borealis Great Wall, the largest single contiguous structure ever identified in the observable universe. Initially mapped through the statistical clustering of highly energetic gamma-ray bursts, it is a massive galactic filament stretching across roughly 10 billion light-years of space. Yet, despite its incomprehensible length, the wall itself is incredibly thin. The mass along its length is arranged in a highly compressed sheet, flanked on all sides by staggering volumes of absolute emptiness. When the total mass of the observable universe is integrated across its entire volume, the luminous matter fills a statistically insignificant percentage of the spatial geometry. Everything else is void. Furthermore, these underdense regions are not passive spatial gaps. They are active, dynamic drivers of cosmic evolution. As the metric expansion of space continues, the residual matter inside a void is subjected to an outward velocity vector, actively draining into the surrounding high-density walls. The superclusters grow denser, while the voids grow progressively emptier. This kinematic evacuation accelerates the density contrast across the cosmic web. Voids do not merely exist. They actively develop, they merge, and they exert a repulsive influence on their surroundings through their own internal expansion, acting as an outward kinematic pressure that reshapes the macro-architecture of the universe over billions of years. The Boötes Void is currently in the midst of this active evolutionary cycle, its internal filament slowly being pulled apart as the void continues its slow, billion-year exhalation. While the mechanics of this expansion are mathematically well documented, the standard cosmological model remains entirely incapable of predicting why this specific set of spatial coordinates generated a void of such unprecedented magnitude, leaving an unresolved variable in our data that suggests the initial conditions of the universe may possess an underlying architecture we have yet to comprehend. To fully grasp the implications of this underlying architecture, we must turn the observational lens back upon our own spatial coordinates. We do not reside within the Boötes Void, but empirical mapping of our immediate cosmic neighborhood has definitively established that the Milky Way is situated within a structurally similar underdense region known as the local void. Our galaxy sits precariously at the boundary of this localized underdensity. Beyond the local void, in a vector roughly opposite to Boötes, lies a massively concentrated region of the cosmic web containing the Virgo supercluster, the Centaurus supercluster, and the gravitational anomaly known as the Great Attractor. This immense concentration of mass is exerting a profound gravitational pull, dragging our entire local group toward it at a systemic velocity of hundreds of kilometers per second. This localized dynamic opens the door to a much more profound and actively debated question within contemporary astrophysics. Are we merely sitting at the edge of the local void, or is our entire cosmic sector enveloped within a vastly larger, unmapped underdensity? The hypothesis that our observational vantage point is deeply embedded within a colossal void has been the subject of intense academic scrutiny. This proposed megastructure is designated the KBC Void, named after astrophysicists Ryan Keenan, Amy Barger, and Lennox Cowie. Through rigorous observational papers published between 2013 and 2020, their research team presented compelling spectroscopic data arguing that the localized density of galaxies surrounding the Milky Way, measured meticulously out to a radial distance of approximately 1 billion light-years, is demonstrably lower than the mean cosmological density by roughly 20%. If accurate, this structure would span an astonishing 2 billion light-years in diameter. It would encompass the Milky Way at or near its geometric center, unequivocally standing as the largest underdense region ever identified in the observable universe. While alternative datasets suggest the density contrast may be less pronounced due to potential calibration variations, astrophysicist Indraneel Banik at the University of St. Andrews has continued to publish extensive analytical frameworks, as recently as 2024, arguing adamantly that the KBC void is a physical reality. The theoretical consequences of residing within a 2 billion light-year void are extraordinarily significant. If our planetary observational platform is located near the core of a massive underdensity, then our localized measurements of cosmic expansion are not objectively sampling the universe as a whole. Instead, they are measuring the localized kinematic behavior of matter within a specific gravitational environment. According to general relativity, matter located inside a void is subjected to a net outward gravitational pull exerted by the higher density walls that form the void's perimeter. This outward radial acceleration effectively compounds the baseline metric expansion of space within our local neighborhood. Consequently, when we measure the recessional velocities of relatively nearby galaxies, the universe appears to be expanding at a slightly accelerated rate compared to the true, global expansion rate of the cosmos. This localized kinematic distortion holds the potential to partially, or perhaps entirely, resolve one of the most critical anomalies in modern theoretical physics: the Hubble tension. The Hubble tension refers to the statistically significant, unresolved discrepancy between different methodological approaches used to calculate the Hubble constant. When cosmologists derive the expansion rate using data from the cosmic microwave background, which samples the universe at its absolute largest scales, they arrive at a specific, highly precise value. However, when the expansion rate is calculated using local indicators, such as the luminosity of nearby Type Ia supernovae, the resulting value is consistently and inexplicably higher by roughly 5 to 10%. The existence of a local macroscopic void, actively pulling matter outward and artificially inflating our local measurement of the Hubble constant, could elegantly account for this discrepancy. Regardless of how the Hubble tension is ultimately resolved, the deeper implication remains. The universe we measure from our terrestrial vantage point may not be an accurate representation of the universe as a holistic entity. This realization forces a critical reevaluation of the core philosophical bedrock of cosmology. Since Albert Einstein formalized the cosmological principle in the early 20th century, the discipline has operated on the foundational assumption that our location in the universe is not privileged. The cosmological principle dictates that at sufficiently large scales, the observations we make from Earth should be representative of what observers anywhere in the cosmos would see. However, the empirical discovery of massive structures like the Boötes Void, combined with the plausible hypothesis that we ourselves are navigating the interior of an even larger underdensity, deeply complicates this foundational assumption. We are peering at the universe through a potentially distorted observational window, burdened by the gravitational biases inherent to our location. Acknowledging this localized bias does not imply that the standard lambda cold dark matter model is fundamentally incorrect. It has been rigorously validated through dozens of independent observational vectors. What it implies, rather, is that our standard model may be functionally incomplete when applied to specific directional vectors. The localized texture of the universe possesses a radically different geometry than the universe averaged over its entire visible volume. When we analyze this texture honestly, prioritizing empirical data over historical assumptions, we must conclude that the defining characteristic of the universe is not matter, but emptiness. If voids are as central to the structural integrity of the cosmos as recent surveys suggest, then the universe is fundamentally an architecture of nothingness, with extraordinarily thin, luminous walls of baryonic matter draped precariously across its surface. The Boötes Void stands as the clearest, most unambiguous single example of this cosmic texture that we currently have the capacity to study. More than 4 decades after Robert Kirshner and his colleagues first published the anomalous redshift data that hinted at its existence, the Boötes Void remains the subject of intense academic investigation. Peer-reviewed papers analyzing its internal filamentary structure, its sparse galactic content, and its broader implications for cosmic topology continue to populate the astrophysical literature year after year. The void has not faded into the background of established science, because the fundamental physical questions it raises have not yet been adequately answered. The current void merger model can elegantly describe the kinematic process of how the void grew over billions of years, but it cannot fully explain the precise initial conditions in the primordial plasma of the early universe that were required to seed a void of this exact, staggering magnitude at this specific spatial coordinate. To contextualize this absence, without relying solely on abstract mathematics, one simply needs to look up at the constellation Boötes on a clear night. The constellation is easily identifiable by locating Arcturus, the 4th brightest star in the night sky, a highly luminous red giant, situated roughly 37 light-years from Earth. When you observe that kite-shaped geometric figure, you are looking past the immediate foreground stars of our local galactic neighborhood. Behind those faint deep-sky objects, there lies a region of deep space, spanning several degrees across the sky, that is almost completely empty. If you possess the capability to ride a photon, traveling outward from the constellation at the speed of light, you would travel continuously for 700 million years before you finally arrived at the edge of an absolute absence. You would then continue traveling at the speed of light for another 400 million years across the interior diameter of the void. During that entire 400 million year transit, you would pass approximately 60 isolated galaxies, all of them gravitationally bound within a single, incredibly thin filament. Depending on the specific trajectory of your transit, you might pass through the entire volume without ever noticing a single luminous object. Only after crossing this staggering abyss would you finally arrive at the far side of the void, where the familiar architecture of the cosmic web would abruptly resume. What you would have traversed is a massive fragment of the universe